Hello everyone, this is Yu Nangao from Dalhousie University. I will present faster path queries in colored trees. This is a joint work with Professor Meng He. First, let me define the problem. The input is a tree with n nodes. Each node is colored in one of c different colors, where c is an integer between 1 and n. Given a query path p sub xy decided by a pair of nodes x and y, we compute the number of colors on the path. In this example, the number of colors on the query path is 4. We are also interested in the path mode queries, which is to find the most frequent color in the path and the least frequent color as well. For example, the mode of p sub xy is blue and the least frequent color is black. You might notice that there is another least frequent color in the query path, which is orange. If there are multiple answers to the mode or the least frequent queries, then simply return any of them. In the batched version, we answer n queries given offline. The computation time includes both the time of pre-processing the input data and the total query time for n queries. It has been proved that all of the 3 path queries share the same conditional lower bound. The multiplication of 2 Boolean matrices can be computed by answering n colored path counting, n path mode queries, or n path least frequent element queries. This means that with current knowledge, the total time of answering n of these queries cannot be faster than time n to the power of 3 halves using the pure combinatorial methods, while saving for polylogarithmic factors. So far, the solution that match the conditional lower bound have been found for all of the 3 path queries. On the other hand, for only a few of them, the results that breaks the conditional lower bound have been achieved. For example, n-colored counting queries on a grid can be answered within time n to the power of 1.41 by reducing the problem to the computation of sparse matrix multiplication, and n-range mode queries on arrays can be answered in around n to the power of 1.48 time using faster min-plus product queries. Inspired by both of these works, we developed faster solutions to batched colored path counting, path mode queries, and path least frequent element queries, breaking the conditional lower bound. Note that the path queries are the generalized versions of range queries on arrays, as shown in the table. Comparing to the mode queries on arrays, our method for path mode queries run a little bit slower. In the remaining time of this talk, we will mainly introduce our method to colored path counting queries. First, we consider a special case that all the query paths are through the root of the tree. Later, we generalize it to handle arbitrary paths. Let x be an integer parameter. Starting from some level t of the tree, where t is less than x, we mark all the nodes at every x levels. Following the pigeonhole principle, the number of nodes to be marked can be bounded by n over x by choosing a proper value for t. Finally, we mark the root of the tree as well. In the figure, the tree contains 33 nodes in total. All the marked nodes are represented by squares. Given that x is equal to 3, by setting t to be 2, we choose 5 nodes from the tree as the marked nodes. And the number of marked nodes is less than n over x, which is 11. Furthermore, a path from any non-root node to its lowest marked ancestor contains no more than x plus 1 nodes. Let p sub xy be the query path decided by nodes x and y in the tree. We use x prime and y prime to denote the lowest marked ancestors of x, y respectively. We use the symbol capital C of some path to denote the color site on that path, and we use p prime sub xy to denote the path from node x to node y, but not including node y. Suppose that the number of distinct colors on the path between nodes x prime and y prime is given. Then for each distinct colors appears on the path p prime sub x and x prime, and the path p prime y and y prime, we check whether the same color appears on the path from x prime to y prime as well, using the path colored amplitude query data structure. Let me explain the query algorithm again using the query path p sub x and y as an example. In the beginning, we create a variable named by result and set result to be the number of colors on path from x prime to y prime. As shown in the figure, there are two colors from x to the child of x prime, which are red and orange, and two colors from y to the child of y prime, which are yellow and pink. Next, we iterate each of the four colors and check whether it appears in the path between x prime and y prime. If the answer is no, then we maintain the value of result. Otherwise, we increment the result by 1. Finally, we return the value of result as the answer. Following the marking strategy introduced in the beginning, for each query path, we only need to call O of x times of colored emptiness queries. And each can be answered in polylog n-time. Therefore, the colored counting query for a single path can be answered in O of x polylog n-time, provided that the number of colors on path between x prime and y prime is given. Storing the number of colors for all pairs of marked nodes x prime and y prime needs O of n over x squared words of space. In addition, the colored emptiness query data structure requires additional O of n words of space. The remaining question is how to compute the number of colors on paths between all pairs of marked nodes efficiently. Note that so far we haven't used the property that the query path is always through the root. Let symbol perp denote the root of the tree. We construct a Boolean matrix A with n over x rows and c columns. Recall that c denotes the total number of distinct colors in the tree. Next, we set values for entries in matrix A. Assume that the marked nodes are listed in the pre-order. Entry AIC stores 1 if color C appears in the path between the ith marked node and the root. Otherwise, entry AIC is set to be 0. Matrix A to be created is as shown in the lower right corner. Let M denote the resulted matrix after performing the multiplication of matrix A and its transpose. It turns out that matrix M has n over x rows and columns, and each of them corresponds to a marked node. In this example, the second row of matrix M corresponds to marked node x prime, and its fourth column corresponds to marked node y prime. And the entry I'm13 stores 1, which indicates that the intersection site between the colors on the path from x prime to the root and the colors on the path from y prime to the root contains a single color. Let's go back to see the input tree. Indeed, the path from x prime to the root and the path from y prime to the root share a single color, which is green. Note that Not all the entries in matrix M are of interest. If two marked nodes whose lowest common ancestor in the tree is not the root, then we can simply discard the matrix entry in M that corresponds to this pair of marked nodes. Assume that the number of colors in the path from each marked node to the root is given. Given that the matrix M is available during the query procedure, we can use the inclusion-exclusion principle to compute the number of colors in the path between two marked nodes in constant time. Again, this result is correct only if the lowest common ancestor of this marked nodes is the root. By and large, as long as we know the entry values in matrix M, then we can compute the number of colors on the path list for all pairs of marked nodes that are of interest. However, matrix A could have as many as C times n over x non-zero entries. As a result, there is no efficient way of computing the multiplication of matrix A and its transpose directly. Instead, we construct a new matrix, height A, with a bounded number of non-zero entries. Given a marked node xi, we define a color set height C of xi to be the set of colors that appear on the path from xi to x prime I, but not appear on the path from x prime I to the root. Recall that x prime I represents the lowest marked ancestor of xi. And entry height AIC stores 1 if color C appears in color site height C of xi. For example, in matrix height A, the third row corresponds to the marked node x2, and the green path in the tree starting from marked node x2 has two distinct colors that do not appear in the yellow path starting from the node x2, x prime 2 to the root. And the two colors are orange and red. Therefore, the third row of matrix height A has two non-zero entries. The matrix height A has at most O of n non-zero entries, since the matrix has n over x rows, and each row contains at most x non-zero entries. Let height M denote the matrix by multiplying matrix height A and its transpose. Given that the number of non-zero entries in height A is bounded, we can use the sparse matrix multiplication technique to compute matrix height M efficiently. And entry height M ij stores the number of distinct colors in the intersection site of color sites height C of xi and height C of xj. Recall that we are aiming at computing an n over x by n over x matrix denoted by M. It turns out that matrix height M can be turned into matrix M, and the transformation takes only O of n over x squared computation time. We leave the details to our paper. So far, we have seen a data structure that can be built efficiently using sparse matrix multiplication for authoring color counting over query path through the root of the tree. Next, we consider color counting over arbitrary query paths. The technique we apply is centroid decomposition. A centroid is a node in the tree such that after removing it, each resulted subtree contains at most n over 2 nodes. We observe that a query path is either contained within a subtree with no more than n over 2 nodes, or a path is a path through the centroid. After removing the centroid of the tree, we process each resulted subtree with no more than x tree nodes recursively. And after log n over x recursive level, each subtree that is newly constructed contains no more than x tree nodes, and we stop there. We refer to a subtree that contains at most x nodes as a base component. In this example, parameter x is set to be 3, therefore the base component contains at most 3 nodes. And the tree in the left-hand side shows the recursive tree with log n over x levels. Next, we assign weights to each node in the tree. In general, the centroid removed at recursive level L is assigned to a weight L, where L starts from 0. And all nodes in the final base component are assigned to weight infinity. We construct a data structure for path minimum queries upon the new weighted tree. A path minimum query is to find a node that carries the smallest weight in the query path. Given a query path, we find the node with minimum weight. According to this node, we can find its corresponding component in the recursive tree. As shown in the figure, the minimum weight in the query path is 1, which indicates that the query path must be contained in a component in the second level of the recursive tree. And the query path must contain the centroid of that component. If the minimum weight in the query path is infinity, then the query path is completely contained within a base component. Therefore, the query path must contain no more than x nodes. And we can iterate each node in the query path and count the number of distinct colors on it in O of x polylog n time. Since the query path is through the centroid of the component, we can make some transformation upon the subtree in that component and turn it into a new tree that is rooted by its centroid. The transformation is simple. We reverse each edge in the path from the centroid to the root of the subtree. As a result, the query path is now through the root of the newly constructed subtree. Then we can use our method introduced before to answer the colored counting queries over the query path. That is through the root of the new transformed tree. Overall, to generalize our method for supporting queries over arbitrary paths, we build a data structure that increases the space cost and the pre-processing time by a factor log n over x, while maintaining the upper bound of the query time, which is O of x polylog n. We leave the details of our solutions to batched path mode and batched least frequent element queries to our paper. For path mode queries, similar to mode queries on arrays, we reduce the problem of computing min plus product. For mode queries on arrays, the matrix to be used is a moment matrix, namely, at each row the matrix entries are non-decreasing. In the paper SODA 2020 and ICOP 2021, they applied a special structure of moment matrices and designed a fast method for computing the min plus product. However, the matrix used in path mode query is not a moment matrix. Fortunately, we observed the special structure of the matrix that is inherited from the tree topology and use it to achieve an efficient method for computing the min plus product as well. For batched least frequent queries, if we apply the same method as over computing the mode, we might return an element that never appears in the query range. For example, we might find an index k star such that the sum of a sub I k star and b sub k star j is 0, where the sum represents the number of occurrences of element k star in the query path. To avoid this issue, we adjust the existing method for computing the min plus product. After adjustment, within the same amount of query time, we can also find another index k star star such that the index k star gives the second smallest sum. So if the smallest sum is 0, then we can simply return the second smallest sum as the answer. In the full version of this paper, we make our static data structure dynamic using the global rebuilding technique. Our dynamic data structure can support each update or query operation in little o of n to the power of 2/3 time. Finally, we conclude this talk with an open problem. Although we break the conditional lower bound of path model queries, comparing to batch model queries on arrays, our computation time is clearly slower. The question left is, can we close the gap of computation time between them? That's the end of the talk. Thanks for your attention.